Hello viewers, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. In today's class, we will discuss about column space of a matrix. So in this class, first let us quickly recap the definition of vector space, subspace, and some subspace theorems which are useful today, and quickly recap the null space of the matrix. Later, we move on to column space of a matrix, today's topic. And we will complete a theorem on column space of an m by n matrix is a subspace of Rm. Later, we solve some of the problems on column space, and we will discuss the difference between null space A and column space A. Let us quickly go through the vector space definition. A vector space is a non-empty set V of objects called vectors on which two operations called addition and multiplication by scalars are defined by the following 10 axioms. For all uv belongs to uvw belongs to V and scalars C and D, we need to have the following 10 properties. This is the first one. U plus V belongs to V, closure property with respect to addition, and this is commutative property with respect to addition. U plus V is equal to V plus U, and associative property with respect to addition, and this is zero element, zero vector must be there with respect to addition in the set, and for each vector U in V there must be a negative minus U in V such that U plus minus U is equal to O, zero vector, and the scalar multiple of U by C, which is denoted by UC, must be in V, in the vector space V, that's set V. C times U plus V is equal to CU plus CV.
And the eighth property is that C plus D times U is equal to CU plus DU, where C and D are scalars and U is a vector. And the ninth one is C times DU is equal to CD times U, where CD are scalars and U is a vector. And finally, 1U is equal to U. If all these 10 axioms are satisfied in a set V, we can say that V is a vector space.
And subspace itself is a vector space and subset of a vector space V, which has three properties. The zero vector must be in H, and it must be closed under vector addition, and H must be closed under scalar multiplication. If these three properties are satisfied and H is a subset of V, then we can say that H is a subspace of V. And later we gone through these points in our earlier classes. Any sum of scalar multiples of vectors is called linear combination of vectors. And span of V1, V2, and so on Vp is the set of all vectors that can be written as a linear combination of V1, V2, and so on Vp. That is the mathematical definition of span of V1, V2, and so on Vp is equal to set of C1, V1 plus C2, V2, and so on Cp, Vp, where C1, C2, and so on Cp are scalars. This is another theorem we have already seen. If V1, V2, and so on Vp are vectors of a vector space V, then span of V1, V2, and so on Vp is a subspace of V. These are the statements which we are going to use today. And in the previous class, we have discussed about the null space. The null space of an m by n matrix written as null A is the set of all solutions of the homogeneous equation Ax is equal to O. the null matrix. That is, null A is equal to set of X such that X belongs to Rn and Ax is equal to O. So null A is a set of all X belongs to Rn that are mapped onto the 0 vector of Rn. The null space of an m by n matrix A is also a subspace of Rn. This is what we have seen in our previous classes. So we quickly gone through those items for ready reference for this class. In today's class, we will discuss about the column space of a matrix. In the previous class, we have seen the null space of a matrix, which is useful to find the solutions for homogeneous equations. And the column space of m by n matrix A is the set of all linear combination of the columns of K. This is the column space. It is denoted by column space A. We call it as column space A. This is the symbol, capital COL A. Call A. Columns. We call it as column space A. Let us see how it will work. If A is equal to, A is a matrix, it's a matrix of A1, A2 and so on An, where A1, A2, An are columns of the matrix. Then column space of A is equal to span of A1, A2 and so on An. Here each vector, each column is a vector. Each column of the matrix A is a vector, and these n vectors are taken into a set, and span of that set is column space A. Let us explain this using a simple problem. Let A is equal to -2, 4, -1, 2 and W is equal to 2, 1. Determine if W is in column space A. Is W in null space A? This is the problem. So let A is equal to -2, 4, -1, 2 is equal to matrix of A1, A2, where A1 is the first column and A2 is the second. So A1 is column matrix -2, -1 and A2 is equal to column matrix 4, 2. We know that column space of A is equal to span of column matrices of the given matrix. So here we have two column matrices, that is A1 and A2. So column space A is equal to span of A1, A2. So the linear combination of these two columns, or simply we call it as vectors, will be the column space of A. That is, all possible vectors or all possible column matrices with these two, with the linear combination of these two columns is the column space of A. Now W is given as 2, 1. This is nothing but minus A1. If you multiply this A1 with -1, we will get W. So W can be written as a linear combination of these two, as W is equal to -1 A1 plus 0 times A2. So here -1 and 0 are my scalars, are weights here. So now it is in the form of W is equal to C1A1 plus C2A2. Here C1 is -1, C2 is 0. So W is a linear combination of A1 and A2. So W is in column space A. So this is the first problem. Now let us check whether W is in null space or not. Null space of A. To check whether it is in the null space or not, we have to multiply A and W. A is the given matrix, W is the given vector. So after multiplying these two, we can get a zero vector, a simple zero vector. -2 into 2 minus 4, 4 into 1 is 4, -2 and +2. So it's zero vector. We got a zero vector. So since we got a zero vector, AW is equal to null vector. It implies W is in the null space of A. So to check a vector whether it is in the null space or not, just we have to multiply with the given matrix. To check whether it is in column space A, we have to check whether it is a linear combination of the columns of given matrix. So let us move on to one more problem. Let A is equal to 10 minus 8 minus 2 minus 2 0 2 2 minus 2 1 minus 1 6 0 1 1 0 2 and W is equal to 2 2 0 2. Determine if W is in column space A and W is in null A. So similar problem, but the order is 4 by 4 matrix is given to you. So again, A is equal to matrix of A1, A2, A3, A4, where A1, A2, A3, A4 are the columns of the given matrix. A1 is the first column, 10, 0, 1, 1. A2 is the second column, A3 is the third column, A4 is the fourth column. So the given matrix A can be written in this form. So now we have to show that this is a linear combination of these vectors, these four vectors. If it is so, W is in column space A. So we can observe that W is equal to nothing but A1 plus A2. If you add the first two columns, you will get W. So W can be represented as a linear combination of these four vectors as W is equal to 1 time A1 plus 1 A2 plus 0 A3 plus 0 A4. Since column space A is nothing but the span of these four vectors, so W is a linear combination of these vectors, and since it is a span of these vectors, we can say that W is in column space A. So let us now check whether W is in the null space or not. To check whether it is in the null space or not, just we have to multiply A and W. After multiplication of this matrix carefully, since it is 4 by 4, you will get 20 minus 16 plus 0 minus 4. So 20 minus 20 is 0. Similarly, 0 into 2, 0. 2 times 2 is 4. 2 times 0 is 0. Minus 2 times 2 is minus 4. That is another thing. Similarly, Remaining multiplication also can be done. So you will get this one. See the last one. 1 times 2 is 2. Again 1 into 2 is 2. 0 into 0 is 0. 2 into 2 is 4. 8. So this is not a 0. So this is not a 0 vector. So after multiplication, you didn't get the 0 vector. So this W is not in null A. Is not in the null space of A. So this W is not the solution of the homogeneous equation represented by the given matrix A. So it is a simple check whether we get a 0 vector or not. This is another one. If A is equal to 6 minus 4 minus 3 2 minus 9 6 9 minus 6. Find a non-zero vector in column space A. A is given. A non-zero vector in column space A is to be determined. Let A is equal to given matrix represented by A1 and A2 two column matrices, where A1 is first column and A2 is second column. Then A1 itself is in column space A. Since A1 can be represented as 1 into A1 plus 0 into A2. Since it is a non-zero column, it itself, A1 itself is an example for non-zero vector in column space A. Similarly, A2 can also be written as A2 is equal to 0 A1 plus 1 A2. This is also another example for non-zero vector in column space. Similarly, A1 plus A2. This is 2 minus 1 minus 3 3. This is another example for non-zero vector. Similarly, you can find infinite number of non-zero vectors in column space A using these two vectors. Linear combination of these two vectors, any linear combination of these two vectors is in column space A. So these are the some of the examples of non-zero vectors in column space A. Next, let us prove this statement. The column space of an m by n matrix A is a subspace of Rn. Is a subspace of Rn. In the previous class, we have shown that null space of A is a subspace of Rn. Now it is Rm. So this space, vector space, depends on the number of rows. Null space of a matrix A is a subspace of Rn. That depends on the number of columns. But here, the column space of an m by n matrix is a subspace of Rn. It depends on number of rows. So let us do this in a simple manner. Already we have got the theorem. If v1, v2, and so on vp are the vectors of a vector space, span of those vectors is a subspace. Let us use that concept here. First, let us define column. We know that column A, column space A is equal to span of A1, A2, and so on A. Since here it is a m by n matrix, it has n columns. Each column has m rows. So each column is an m by 1 matrix. Each column, each A1 is an m by 1 matrix. There are n such vectors, n such columns, which are called as vectors in vector space. So here A1, A2, An are the columns of the matrix A, and each column is an m by 1 matrix. So since these are m by 1 matrix, that is nothing but m tuple, these are all elements of Rm. Each matrix can be written as a m tuple or with m rows, m by 1 matrix. So it is these are all elements of Rm. We have already seen that Rn for any n greater than or equal to 1 is a vector space. Since m is also greater than or equal to 1, it is a number, natural number. So Rm is also a vector space. So this is the theorem we have. We know that if V1, V2 and so on Vp are vectors of a vector space V, then span of V1, V2 and so on Vp is a subspace of V. So here this is a vector space and these are the elements, and we are taking the span of these vectors. So this column A is the subspace of Rm using these two concepts. Span of A1, A2 and so on An is a subspace of Rm. So this is what we need to prove. So therefore column A is a subspace of Rm, since this is nothing but column space A. So this is the simple theorem. So we have already proved that null space of A is subspace of Rn. Now we prove that column space of an m by n matrix A is a subspace of Rm. Let us go in detail about column space A here. A typical vector in column space A can be written as Ax for some x belongs to Rn. Any vector in column space A will be in the form of Ax, where x belongs to Rn. So to multiply A with a vector, that vector must be in Rn, since A is m by n matrix. So you have to multiply with some matrix with n rows, so that the multiplication is compatible. So Ax stands for linear combination of columns. So if you multiply A with some vector x, you will get a linear combination of columns of A. That is, in other words, column space A can be written as column space A is equal to set of B. B is a vector here. B such that B is equal to Ax for some x belongs to R. We know that x belongs to Rn implies x is a column vector, that is n by 1. If you multiply the matrix A with n by 1, you will get m by 1 matrix. So B is a m by 1 matrix, a column matrix. All such columns will establish column space. So column space A is the range of linear transformation x to Ax. This will be range. Let us move on to one more problem. Find a matrix A such that W is equal to column space A, where W is equal to set of a matrix 6A minus B, A plus B minus 7B. A 3 by 1 matrix is given, such that AB belongs to R, a set of A elements. So here W can be written as W is equal to set of, here A can be taken out. So A times 6, 1 and minus 7 in the 3 rows, plus B times, here it is minus 1, 1 and 0, such that AB belongs to R. So given vector W can be rearranged in the written lines. So this is equal to span of these two vectors, 6, 1, minus 7, minus 1, 1, 0. Span of these two vectors is nothing but this set. So now W is equal to span of these two vectors. If I have taken these two vectors as columns of some matrix A, then A will be like this: 6, 1, minus 7, minus 1, 1, 0. So these two are the columns. These are the elements of the spanning set. So with the spanning set of columns of A, we can get W. So that is simply written as W is equal to column space. So here this is the required matrix. So this is another problem on null space and column space. Let A is equal to a 3 by 4 matrix. 2, 4, minus 2, 1, minus 2, minus 5, 7, 3, 3, 7, minus 8, 6. If the column space of A is a subspace of Rk, what is K? If the null space of A is a subspace of Rk, what is K? So columns of A are 3 by 1 matrices. So each column is a 3 by 1 matrix. So column space A is a subspace of R3 as per our previous theorem. So K is equal to 3 in this case. Similarly, to find a null space, we need to find a vector x such that Ax is equal to O. To make the vector multiplication compatible, when A is a matrix of 3 by 4, X must have 4 entries. So X is a 4 by 1 matrix. So null space of A is a subspace of Rn. Subspace of Rn, n is equal to 4 here. So it is R4. So K is equal to 4. Or simply you can that this is a 3 by 4 matrix. So column space is a subspace of R power m. M is 3 here. So K is 3. Null space is a subspace of R power n. Here n is 4. So K is 4. Another problem. If A is 2, 4, minus 2, 1, minus 2, minus 5, 7, 3, 3, 7, minus 8, 6. Find a non-zero vector in column space A and non-zero vector in null space. So we have seen in the previous problem, to find a non-zero vector in column space A is very simple. All the columns are in the column space A, since each and every column can be represented as a linear combination of columns. So, to find a vector in column space is simple. Any non-zero column or any linear combination of columns of A are non-zero vectors in column space A. So this is an example for non-zero vector, and this is another example 136, and you can add any two. If you add first two, you will get 6 minus 7 10. In this manner, you can find any number of non-zero vectors in column space A. So to find a vector in column space A is very simple. But to find a vector in null space A is a little bit lengthy. That vector is the solution for the homogeneous equation. So you need to first find out what is null space. So to find the null space of matrix A, we need to find the general solution of AX is equal to O in terms of free variables. To find the null space A, we need to construct an augmented matrix AO. So all zeros in the last column are added to the matrix A. And this can be simplified. We are now trying to convert this equation into echelon form by doing these operations, elementary operations. R2 goes to R2 plus R1. Both these two those are added to get R2. Similarly, R3 gives raised to. Simply we call it as goes to. R3 goes to 2R3 minus 3R1. After performing these two operations, you get this matrix. 2R3. This is multiplied with 2 and subtracted with R1 after multiplying it with 3. So 6 minus 6 is 0. 14 minus 12 is 2. Similarly, remaining elements. So here, this term is to be made 0. For that, we are doing R3 goes to R3 plus 2R2. Here it is minus 1. If you multiply with 2, you will get minus 2. After that, you can add it to get a 0. So we are performing the same operation here. So this will give you minus 10 plus 10 is 0. 9 minus 8 is 1 and 0. Remaining rows are same as it is. And now the effort is to make this one 0. So R1 is added with 4R2 to get this one 0. Remaining columns, remaining rows are as it is. Now here, using this one, we are making these two as zeros. To convert this matrix into reduced echelon form. So here it is 17, that's why it is R1 goes to R1 minus 17 R3. Here it is 4, so R2 goes to R2 minus 4 R3. So third row is as it is, first and second rows are converted as per this row, these rows. And finally, this is 2 and 18. So we are multiplying R1 with 1 by 2 R1 to get simplified equations in the end. These equations are equivalent to x1 minus 9x3 is equal to 0 minus x2 plus 5x3 is equal to 0. This is the second row. And from the third row, x4, this is x4, x4 is equal to 0. So we got the three equivalent equations, which can further simplified as the general solution is x1 is 9x3. So this minus 9x3 is brought here. X1 is 9x3 and x2 is minus 5x3 and x4 is 0 with free variable x3. So the vector x1, x2, x3, x4 can be written as 9x3 for x1, x2 is minus 5x3, x3 is x3, x4 is 0. So after taking x3 as common, 9 minus 5, 1, 0. So null space of A is equal to x3 times 9 minus 5, 1, 0 such that x3 belongs to R. We can replace x3 with some scalar C, of course. So any scalar multiple of this one is a vector of or is an element of null space. So here in this problem we need one non-zero vector. So 9 minus 5, 1, 0 can be taken as a non-zero vector in null space. Or any non-zero scalar, if it is multiplied with this one, this vector, we can get a non-zero vector in null. So it is easy to get a vector in column space A, but to get a vector in null space A, we need to find null space A. Let us move on to one more problem. If A is equal to 2, 4, minus 2, 1, minus 2, minus 5, 7, 3, 3, 7, minus 8, 6. It is a 3 by 4 matrix. Let U is equal to 3 minus 2 minus 1 0 and V is equal to 3 minus 1 3. Two vectors are given. The problem is determine if U is in null space A, could U be in column space A? This is the first problem. So to determine whether U is in null space A, we have to check whether AU is equal to null matrix O or not. So let us calculate AU. AU is after multiplying these two, 2 into 3, 6, minus 8, plus 2 and 0, that will give you 0. Similarly, multiplication of second row with this column will give you minus 3. Multiplication of third row with this column matrix, you will get 3. This is clearly not a null matrix. This is not a 0, 0, 0. So it is not in null space A. So U is not in null A. It is not a solution for the homogeneous equation represented by the matrix A. The next question is, could U be in column space A? So here the columns are 3 by 1 entries, but U is 4 by 1 entry. No linear combination of these vectors, these columns, will give you a 4 entry vector, since all these are only three entries. So you can't get a 4 entry vector with a 3 by 1 matrix. So column space A will be a subspace of R3. You can't find a vector with 4 entries in R3. So U is not in column space A. This is another one. Here, determine if V is in column space A. Could V be in null space? So we have to check whether V is in column space. So to check that, you have to find whether this vector can be formed using these 4 columns, or whether 3 minus 1 3 is a linear combination of these columns. So to get that, let us form an augment matrix A, B, and reduce it to an echelon. So augment matrix AV is equal to this one. The entries of V are added as a last column here to the matrix A. And after elementary row operations, we can convert this into echelon form like this. Echelon form, in the echelon form, 0 entries. Leading coefficients must be 0 entries. These will be 0 entries. Number of zeros are more in the columns, in the rows. So this is in the echelon form. So from this we can conclude that the system is consistent. So you will find solutions for this equation. So this final equation will tell you that x4, this is x4, 17 x4 is equal to 1. You can get the value of x4. After substituting the value of x4 in this one, you will get the values of x2 and x3. After substituting this in x2, you will get the value of x1. So there are many solutions for this. It is clear from the equation Ax is equal to V is consistent. So V is in column space A. If this system is consistent, we can say that it is in column space A. If it is not consistent, we can say that this vector V is not a linear combination of these columns. Since we got a consistent system, we can conclude that this can be formed using these vectors. So this vector V is in the column space of V. Next question is, could V be in null space of V? So with only 3 entries, V could not be in null space of A, since null space of A is a subspace of R4. So it is a 3 by 4 matrix. So to get a null space, to get a vector in null space, you need to multiply with 4 by 1 matrix, since it is 3 by 4 matrix, to make the multiplication compatible. So any vector in R4 can be multiplied with A, and we can check whether we will get a 0 or null vector or not. But we can't multiply V with this A. So V cannot be in null space of A, since it is not an R4 entry. So V cannot be in null space. That is the conclusion. So in this class, we have discussed about column space A and proved that column space A is a subspace of Rm. In the previous class, we have proved that null space A is a subspace of Rn, and in these problems we have observed the difference between column space A and null space A. So with this, I will conclude today's class. Thank you for watching.